So I'm going to work the data screening class example for my advanced statistics course. I'll start by saying this is one of the messiest data sets that I have. The real data set has hundreds of columns that are sort of here, there, and everywhere. So this is a student thesis project that got published, and we are looking at a bunch of different variables, but the ones I included were gender, so that should import itself as a factor because in the CSV file it's labeled with words. Level, so freshman, sophomore, that sort of thing, also should import as a factor. Advising, which is a yes-no variable if they had an assigned advisor, but I left that as integers to show you how to factor variables. And then the questions for one of the scales that we use to assess advising, which is coded 1 through 7. And so as we work through this, we're going to use these columns to data screen just sort of everything. And then as I work it, you'll see that I'm going to save the data set multiple times. And that's mostly because, especially as you're learning R, you will screw something up. And so at different points, I'm going to kind of tell you to create a new data set here. So that means if I mess up something a couple lines later, I can just back up to that last save point. So I kind of think about it like video games. Like, okay, I've saved here, I've gone a little bit, and I've totally screwed up. So I'm going to go back to the last time that I saved, rather than having to do the entire game over again. So the first thing we're going to do is import the data and start with accuracy. So let me go to our studio here. Now I'm going to do something that we probably haven't really done in class, but I'll show you why it's helpful. So I'm going to set my working directory where I have this file saved, so to source file location. What that does is it just saves where I am currently working. Because as you get better at R, you can avoid using this import dataset option. So I could click import dataset from text file, go through and find the file, which I named data screening data, click open, turn on the header, like go through all the options and click import, and that would work just fine. Or I could sort of control it myself by saying, I'm going to start with a data set, just call it imported, so it's read.csv, and then just call the name of the data set. Okay. And that's one line of code that does that whole import clicky button option thing a little bit faster. If you don't like that option, don't do it. Just click import dataset from text file and work through it that way. I like being able to just kind of type it out and be done with it really quick. When you set your working directory, often too it'll change where this folder thing is on mine. Sometimes it does, sometimes it doesn't, but it's supposed to switch the folder down here as well. Alright, so I got the data imported. Alright, so the first thing we're going to do is accuracy. So let's start by following the little hints here. So I'm going to create a new data set called no typos. So I'm going to copy all this real quick, dump it over here so we can not switch back and forth on my screen. So I'm going to create a data set called no typos. So no typos equals, and I call this imported. So now I have a data set that's called no typos. It's the exact same data set. So I could have called it no typos here, but I didn't. Okay, so we've done step 1 here. Now we're going to use the summary function to look at that data set, no typos, and see what the min and max values are, and then I'll handle this factoring thing in a second. So we're going to fix these out of range values first, and then we'll handle that factoring thing. So you can do this in either order. Right. So first thing I want to look at is so see how gender here has labels? Those labels indicate that it imported as a factor. So I'm going to click over here on no typos, the little down arrow. And you see how it says factor with 3 levels? So that's a little weird because it really only should have 2 levels. So one problem is it looks like gender imported with a space. So see how it has a little space here of the levels? We don't want that. And then the level variable actually did the exact same thing. So imported with a space as a variable instead of it just being NA. So there's two ways to fix that. You can fix that by going back to the data set and just deleting all the spaces, or you can fix it on the fly in R, because sometimes opening the CSV files kind of is freaking computers out, so we can just fix it ourselves here. And so that would be any bad factoring problems. So let's actually do that first, since that's the first thing I noticed. Okay. All right, so we're going to fix unfactored or incorrectly factored columns. Okay. So the first problem I see is deal with the space in gender and level. Okay. I also could go through and capitalize all of these so that when I'm making charts or pictures or graphs, they're at least pretty, so I don't have to fix them in a different way. I know we haven't gotten to graphs yet, but when we do, you'll appreciate the factor command. Okay. So to use the factor command, what I'm going to do is do no typos. So it's the dataset name, $, the name of the column, so it's gender, equals factor. Okay. So you can't just type factor and expect it to do something. You have to save it as a factored variable. So I want to overwrite my current gender column with this new information that's corrected. So I'm going to type that again, so no typos, gender, and I'm going to stack my code just to make it a little easier to read. So levels here equals. All right, so the levels has to be what's in the data set that you want to keep. So looking at my summary here, I see that I have female and male, and I want to keep those. I don't want to keep the space, so I'm not going to include it. I have to type it exactly like it is down here. And I can just type male here. If you do not type them exactly the same, right, it will delete them. Okay. I've left off the space because I don't want to keep it. Okay. So the levels command has to have exactly what's in the column. The labels command is where you change it. Okay. And they'll do them in order. So I'm going to go from lowercase female to uppercase female, lowercase male to uppercase male. And I'm going to drop this space, and that's going to go away. So let's try that. Let's look at my summary again. So now I have female and male correctly capitalized, and now the rest of them have become NAs. So that's actually to my advantage because they are missing, but for some reason they imported with a space. I could do the same thing for level here. And I can also sneakily do something else. Oop, you do have to spell a variable name correctly. Turn off the sound. Alright, so we've got the levels currently are freshman, junior, master's, PhD. That's not in the right order. So if you think about this is a variable that sort of has a natural order to it. So I'm going to type them in the order that I want them in. So I'm going to go freshman. They have to be the exact same, like, typed, but they don't have to be in the same order. Then we're going to go sophomore. So one trick, you can highlight a variable name, hit shift and the quotes at the same time, and it'll put the quotes around it. It might save you a little bit of time. Junior. I can type the rest of these. Senior. Master should be next. And then PhD. So those are the levels we want in the order we want them in. Now let's add some labels. You'll see that I also left out the space because I want it to go away. So freshman, sophomore, junior, not that. There we go. Senior, master's, and PhD. Now let's run this. Let me look at my summary again. You'll see now that they're in an order that makes more sense. So this is actually the order that you would go through as you gain more credit hours. And then there are 36 NAs of things that just are people that left it blank. Now the next problem, so these are just kind of relabeling things that are already factored. Now let's actually factor something. So I'm going to factor something that's an integer. So right now advising is listed as an integer. And so it gave me, the summary function gave it to me as a number, but it's not really a number. So if you aren't sure what's in it, you can do a table command, and it's currently 1 and 2. So we're going to change 1 and 2 to yes and no. So same thing, no typos, $sign advising equals. The factor command says the exact same command. You just do it differently. So we got levels equals. So I'm going to do oops, no quotes, 1 and 2. Because that's what's currently in it. So why 1 and 2? Because that's what's in 1 and 2. Remember, these are the frequency, this is the label. And then we want to add labels on top of 1 and 2. So change 1 and 2 to yes and no. Now if I look at that table, it's yes and no. And if I run my summary command, I have fixed it to yes and no. So that's how you would fix factored variables that are factored incorrectly, or actually factor them just in general. So to deal with some accuracy issues here, min and max problems, what we're going to do is I can just rerun summary. I can scroll up, or I can just type it again because we're going to use this a lot. First thing I'm going to do is look for minimum issues. So I'm going to look at min here for each one of these. And question 5 has a 0. So that's the first one I got to fix. So I'm going to do no typos. So I'm going to do this thing, basically. The name of the column, so it's Q5. Square brackets, same thing. No typos, Q5. Okay, you want these two to match. Anytime it's less than 1, that's the problem. Why less than 1? Because if I look at the beginning of the data here, it's coded 1 through 7. So anything less than 1 is a problem. And then in the instructions, I actually said anything below 1 to set equal to 1. Okay. You may just have to set them to missing if you don't know what they're supposed to be. So if I run that, what that does on question 5 is that now the minimum is 1. So I'm going to keep going. Question 8 has a problem. 14. And that's it. So I'm going to do this exact same thing for questions 8 and 14. If I run my summary, now all my minimum values should be correct. Now generally this isn't too much of a deal if you get data from online, like let's say you're using Qualtrics or SurveyMonkey or some sort of software. But often what the real issue is that, let's say you have a scale that's supposed to be coded 0 through 4, and you forgot to fix it on Qualtrics, and it just will automatically label it 1 through 5. So that's a time when you might have to fix it because it's not that the scores are incorrect, it's just they're labeled inappropriately, and so that's where a factor command might be useful. Or there's a recode command in the car library that would help. Alright, so I did min, let's do max. So anything over 7 we're supposed to set to NA. So question 2 is the first problem. So greater than 7. And we're going to set those to NA. So now question 2 has some more NAs, but nothing over 7. So it's 9, 13, 14, and 15. And then that's it. And 15, and then change them over here too. 9, 13, 14, 15. Okay, there are much more efficient ways to do this where you can scan all of the columns at once. But I think when you're first starting to learn R especially, it helps if you just like sort of think about it like manually, one question at a time. But there are ways to do this a little bit faster if, let's say, you have 200 columns that all have the same rules. But for our purposes, we're kind of like learning what this is doing. So that's why I have you do it one column at a time. So if I check out my summary now, it looks like I don't have any under 0 or, I'm sorry, under 1 or over 7. So we are done with accuracy. So let us move on to missing data. Missing data's got a lot of notes here because it's not complex in the sense of like what I'm doing. It's just the way to get to where we want to be takes a little bit of work. So, missing data. Alright, so what we're going to do is create a couple of new data sets by partitioning off participants based on these rules. And this is the difference between missing not at random and missing completely at random. So the first thing I have to do is calculate missing values for participants and for variables. So we're going to start with participants for reasons I'll get to in a second. So we're going to run this function. This does not change. It's just a little function that I wrote that calculates a percent of the number of NAs. So it sums the NA, so is NA, divides by the length, multiplies by 100. So this is going to be percent, hence the name of the function is percent. Okay. So starting by participants, we're going to run this line. Okay. So we're going to call it missing. The data set name is no typos currently still. Okay. The apply function, what it does is it, keep this here, it has the name of the data set, 1 for rows, 2 for columns, and then the name of a function you want to run. So if I wanted to see each participant's average score across all columns, which it would be a little weird since we have gender. Oh, it's not going to like this. So let's say columns 4 through 26. So if I wanted to create an average score for each person, I could use mean. Right. So that would create me an average score across all of these different participants. Okay. And so what it's doing is it's taking the data set name, 1 for rows, so do this by row, 2 for columns, and then calculating a function, which we defined as give me a percent of missing values. So calculate that, and let's look at missing. So the missing values here are, these first couple of people are missing none. This person's missing 88% of their data, which is like pretty much all of it. Some people are missing 100%, so 96. Some people are 3%, so they're only missing one variable. And so the first thing we have to deal with really is sometimes people just quit an experiment. So they open it up and they're like, screw this, I don't want to do it. So they quit. That's missing not at random, but it's not a problem like with your scale, it's a problem with the participants. So we're going to exclude participants who are missing data just because they quit the experiment. And then we're also going to exclude participants who are missing more than 5% of their data. And so we can kind of treat these the same. So we're going to just say, okay, they're missing more than 5% or they just quit in the middle. And that's imnar. So we're going to create a couple data sets. So we're going to do replace people here. So these are people that I can replace who are missing less than or equal to 5%. So this is no typos. Which I use this code a lot, so I don't know why I can't type it today. So that's 270 people that I can replace or do something with because they're missing less than 5% of the data. And then I'm going to do sort of the opposite of that and call this no people. So these are people I don't want to replace because they have too much missing data. And you will see that no people and replace people should add up to the total number of lines in your data set. If they are more than that, you've done something wrong. Okay, so 97 plus 270 is 367. Now some people, sometimes we may never use these no people again. Like we may decide that they're just missing too much data and just never use them again. But if I have like 3 hypotheses that I'm testing, they might have enough data for one hypothesis but not another, and we want to keep them around so that we could use them again if we wanted to. Now we're going to calculate by columns. So participants you calculate by row. For variables you calculate by column. And what that does is it gives me a list of percentages for each column. So Vising clearly has more than 5% missing, which is bad. We don't want to replace that. But all the rest of these are less than 5%. Okay. So I'm really just kind of figuring out which variables are the problem. Okay. And so I want to create 2 more mini data sets. And here's how I'm going to do that. I'm going to do replace all are the people that I can replace and the columns that I want to replace. Okay, so replace all is, I'm going to keep using my replace people part here. So don't use no people. Those people we're just not doing anything with. That's why that has no. So I'm going to use replace people, and I want to replace the columns that I can. Okay. I'm not supposed to replace categorical columns that are demographic variables. So gender, level, and advising. It will estimate those for you in a categorical way, but it's probably not a good idea to guess at someone's gender. So I'm going to exclude that. Thankfully, that's the first 3 variables I want to exclude. Everything else I want. And so one function, I don't think I've taught you yet, but you can use the names function. And you type in the name of the data set. And so the names function gives you all the names of the columns in order, and it also gives you a marker so you can count. So this 1 here means gender's number 1. This 11 here means this is the 11th variable. 21 means this is the 21st variable. So I can count 1, 2, 3. I want to start with column 4 and end with column 21, 2, 3, 4, 5, 6. So I want columns 4 through 26. I don't need a C function for that. 4 through 26. You can put the C around it, but you don't have to. For no column, because we're not replacing them, we still use replace people, and I want basically everything else. So I could do negative 4 through 26, or I could just do 1 through 3. Okay. Either way, your replace all and no columns should add up to the number of columns in the replace people data set. So I've got 23 columns plus 3 columns. Okay. So don't drop columns because you'll need them later. So here's an example. Question 1 has no missing data. So it seems perfectly reasonable to just ignore it for right now and say, okay, well, I need to replace question 3, question 9, 13, 14, 15. And so I'll just include those in the replace one because they're the only ones that need data replacement. The problem with that is basically with this coding system that I'm teaching you, those columns are gone, like forever in a sense. So we're going to keep them together with their partners. I can replace all of these because they have 5% or less. And it's okay if the column has 0%. Mice will just use it as an estimator. And so essentially by keeping all of this participant data together, I have a way of better estimating because it uses the entire data set. I don't want to include these because I don't want them replaced, and they're categorical, so I could have left in gender and level, but it's just easier to separate out the categorical ones so that you don't ever try to replace them. But keeping them all together, one, allows you to keep them together for the rest of the data screening, but it also allows you to make sure that you're estimating based on the most amount of data that you have. And if you have no missing data completely, you would skip the mice section we're about to do. Okay. So the important component here is that as you're separating people out, make sure replace people and no people add up to your total of original number of people, so 367. And then as you separate your columns out, the columns all stay in one data set or another. So my no columns and my replace columns are 23 plus 3. So moving on from creating these separate data sets, now we have everything we need to start replacing missing data. So first thing you want to do is be sure you install the mice library. Mine's already installed, so I'm just going to open it. right? And then MICE is a package called multiple imputation chained equations. It will import based on or estimate based on a iterative procedure that's sort of Bayesian Markov based. So we're going to create a temporary data set called tip-no-miss. And it's temporary because what happens when you run MICE is it creates you actually a bunch of data sets. So it's going to run down here and iterate for a little bit and see how it's here under values and it's like a list. So there's actually a bunch of stuff in there. So what's happening is it's creating a bunch of missing replaced data sets. So I have to tell it to complete the data sets. Remember, this was a typo in the original document, so make sure it says complete and not compete. And so I take tip-no-miss and I put a 1 here. This number could be 1 through 5, which is MICE auto defaults to creating you 5 missing data sets. And I just picked 1. You could pick any number as long as it's 1 through 5 without changing this line. And that will combine the missing data back into your original data set. So that's basically telling it which missing data set you want. And so now I have a replaced one that has no missing data. So I can check that real quick if I wanted to. So I could say summary replaced and see how there are no NAs. Our replace people, or replace all rather, does have NAs. So it's got a couple of NAs here and there. And then our replace data doesn't have any, which was the point. Okay. So now I'm going to combine everything back together. So all of the columns get combined together. And in class I did we did cbind and then replaced, can't spell, and no column. And that puts the original columns back at the end. You can do this the other way. You can do it in whatever order you want. Right? I kind of like having my my categorical problem data either at the beginning or the end. And in this particular example, I just did it at the end, so I'm going to keep doing that because that's what you did in class. But don't forget, you can switch that around to whatever order you want it to be in. Okay. Oh, it didn't like that. Oh, not replaced. Sorry, there we go. So my all columns data set now has 26 variables, which is what I wanted. And I have to combine the columns back together first because otherwise I don't have the right number of columns to put the rows on. So you can kind of think of this as like cutting up a piece of paper or a cake or Legos is the example I used in class. You have to have the same number of rows to put columns together and the same number of columns to put rows together. So we split it up by people, then columns, so we have to put it back together in the reverse order. Now I'm going to create all rows. And that's all columns plus the people. So all rows has all 367, even including the people we couldn't replace. And both of them have all columns. For everything else, I'm going to use all columns. You would use all rows when you had participants that had too much missing data on one scale, so you couldn't replace them, but they had all the data on this other information, and you wanted to use them in that analysis. So this would be like if you had multiple hypotheses, and they have enough data in one area, I can replace them, but not in another. So I would keep them with the data set so I could use them on the analyses they had data for. Okay, because in every data analysis we're going to talk about, I'm going to show you how to exclude people who have NAs. So it isn't a problem that I've combined them back together. For this example, I'm going to do all columns though, just because I'm matching this example. Alright, so we did missing. Let's move on to outliers. Here, I'll just copy everything. That does make it a little easier. Alright, so now, outliers, where does it start? Ah, there it is. Okay. So the first thing I'm going to do is create some Homoscedasticity distance scores. And I'm going to do that using this crazy code, and I'll try to talk you through what's going on here. So I'm going to save it as Mahal. The function is Mahalanobis. And Mahalanobis requires that you first tell it what data set you're going to use. So I'm going to use all columns. Okay. Then you have to tell it how you're going to center it. So we're going to use call means, which is a function that tells it where the center is. So remember, Mahalanobis is about the centroid, the middle of the middle. And so that is saved, or that is calculated by using column mean. So it's going to calculate the mean of each column. So we're going to do all columns, but we cannot include categorical variables because this doesn't calculate the average of a nominal score of like a gender column. So we're going to have to drop the columns that are problematic. Well, with my new data set, I put them on the end, so I have to figure out where those are. Don't forget, you can use the names function to look at the names of everything. And this is especially helpful if you have lots of columns. One morning over here, if you have lots of columns, sometimes it just won't show you all of them. So names will at least, give you all of the names in the data set, even if they don't show here because there's like 300 columns. So this is 22, this is 23, so it's 24, 25, and 26. So I'm going to drop those because otherwise this won't run. And then the last piece is covariance. So covariance is essentially kind of like it's an unstandardized correlation table. It's not kind of, it's an unstandardized correlation table. And what that does is it calculates the relationship between the columns as well. Okay, so this is how it calculates how far away everyone is. So I'm going to use all columns again, minus C24 to 26. And the only thing I've forgotten is that that's the data set as well. Okay, so all three of these should match. Now, if you have any missing data, it will throw up at you. We don't in this data set. Well, actually we do, but not in the columns it's looking at. So just in case, I want to do na.rm equals true. So remove NAs, just in case that's a problem. And then in my covariance one, I'm going to do use equals pairwise.complete.obs, which is the function that will exclude people when you need to, but not other times. And including this all the time will just keep you safe from running into an NA error. So if you ever get NA out of this, that means it likely didn't like a column you were using or has missing data and just gave up. So what that did was calculate me, let's look at them, for each participant, a list of Mahalanobis scores. Okay, so I said all columns, right? Okay, so the numbers here, just as an aside, are the original participant number line. So you see how it skipped 4 and 5? That's because 4 and 5 got excluded somewhere. Okay. And it's the distance from the mean of the means. So small numbers mean they're very close to the centroid. Large numbers means they're further away. And the large number are the people we're going to get rid of. Okay. So we're going to have to come up with a chi-square distribution cutoff score because chi-square is how Mahalanobis is distributed. So we're going to use this line here, Q chi-square, so come up with a cutoff score where it's 1 minus alpha. So we're going to want 0.001 in the tail. Remember that 001 is our rule for data screening. That's the big important rule. And we do 1 minus 001, otherwise it would give me 001 on the bottom. And that would be like basically everybody. So we want to use 001 in the tail, like in the right side of the distribution, the really crazy people, they're really far out there. So if they're less than 001, they're in the 0.999 percentile. So we're looking for people whose scores are really, really wacky. Okay. In call, and then basically it's the same code right here. So you can just kind of copy this and use it a couple times. So we still have to drop those columns, because if we don't use them here, we shouldn't use them here. In call calculates the number of columns that you're using. So let's see, that means our cutoff score is 4973. Now on the homework, sometimes you're going to get asked, what is the cutoff score? Well, or what is the degrees of freedom for the cutoff score? It's basically this thing right here that's calculating the degrees of freedom. Because the way that this function works is it's p-value degrees of freedom, but we've told it to add up the degrees of freedom for us. And that's 23 degrees of freedom for 23 question columns. So the degrees of freedom are the number of items that go into the cutoff calculation, not in -1. That's one of the most commonly missed things on exam question or test questions is degrees of freedom is in -1. That is true for a lot of statistical tests, not for this particular outlier procedure. It's just the number of columns you used. All right, if you get asked what's the cutoff score, I can look over here, see undervalues, or I can just run cutoff, see that's 49. If I want to tell, you get asked how many outliers are there, just run a summary of Mahal less than cutoff. Okay. So that's asking how many people's scores are less than the cutoff score, and I'm doing it like this for a reason. It seems a little backwards until here in a minute. Okay. So there are 242 people who are less than the cutoff and 28 that aren't. So we're going to exclude the outliers, the falses. And the reason why I have you do it like this here, although it probably makes more sense to do it the other way, is that when you subset, you want people's scores who are less than the cutoff. And so I think it's a little confusing to ask people to say how many are greater than the cutoff. Okay, now subset less than the cutoff, and it tends to confuse people. So we just do both as less than the cutoff, remembering that false is the number of outliers. So we should go from having 270 participants in our all columns, minus 28, was 242, right? Yeah, so we should have 242 people left when we're done. Oops, I should type up here. So no out for no outliers, 242 people. All right, so let's do assumptions. First assumption is additivity. Ooh, that was about to be a bad word. We're gonna make a correlation table. So do coral. You can call it whatever you want. Cheese table, but I'll call it coral for correlation table. So the function is cor, C-O-R. We did R core when we were working on correlations, but that's really for significance because it gives you P. Core will give you all of them at once, and it's R core will as well. But this allows you to do symbols for numbers, which is a handy function that will allow us to see a little better if we have any problems. Okay, I'm going to copy this. So you're going to use this columns minus categorical thing a lot. So I've saved my correlation table. Now I can view the correlation table, but it's insane. With 23 questions, it goes on and on and on. And then it would take a lot of scanning, and you'd have to sit there and like scroll through each one. So the simplest thing we can do is do sim num. So symbols for numbers. And then we put in our saved correlation table. Now this is still a little well, okay, mine came out very perfectly right now, but it doesn't always come out this pretty. And what you're looking for is anything with a star or a B. So the ones will be labeled as ones, and now that one down the diagonal is supposed to happen because that's it correlated with itself. Okay, that's gonna stay. A B means it's correlated at 0.95 to 0.1 or to 1. A star means it's 0.9 to 0.95. And so we've got a couple little pluses. Those are 0.8 to 0.9, but that's okay. So remember the rules. Anything over 0.9 is bad. Lots of commas, lots of dots. So these are questions on a scale, and they're supposed to be related. So it isn't too surprising that we see lots of symbols. But we're looking for stars or Bs. And I don't have any, so nothing's wrong. So I do not have to do anything here. Drop or average any columns that are too highly correlated. Well, no need. So I'm going to create myself a final data set from my, oops, I used the wrong one. It even says right there in the notes, and I complained at you guys for not reading. So I can complain at myself. Should have used no out here, right? Because that's the last data set I had here. All right. I still have some pluses, but I don't have any B's or stars. So I'll create myself my final data set, and just rename it final from no out. All right. So we're going to run a fake regression analysis because we're not doing any particular type of data screening at the moment. So we're going to first kind of set up the rest of the assumptions. So the first thing I'm going to do is create a random number to compare against. So I'm going to call that random. So it's r chi-square, which stands for a random number from the chi-square distribution. You have to tell it how many rows there are, so we're doing in-row final here. And then a degrees of freedom. Why 7? It works. 7's been my lucky number for this particular thing for a long time, but really you need to pick anything above 2, because that gives you enough variance. In row just makes sure we have the same number of rows in the random one as final, otherwise this will freak out. So all that did was create me a random set of numbers. Great. And everybody will get slightly different random set of numbers because that's the point. So your picture and your neighbor's picture may not look the same. Also, mice is not random, but it is an imputation, so it'll be slightly different for some people. So at this point on out, we may get different pictures even though you're running the exact same code. It shouldn't be too wildly different. So for outliers, I had 28 just then, but you may have gotten 26 or 27 or 29, just kind of depending. So there might be people who are really close to our cutoff score who in your mice data set were outliers and my mice data set just barely weren't. And that's why with outliers, I normally talk about like, throw them out, they're really crazy. If you have a really small sample, be careful with that. Okay. So we're going to run a fake regression. I'm going to call it fake so I know it's fake. I'm going to do random, which is y, equals dot. So what's going on here? In t-tests, what we did was dv approximated by iv. So dv tilde iv. What we're doing now is we're saying, let's predict all of our variables with use them to predict a random number and make sure that everything we get is randomly distributed, which means that it's probably approximating normal, linear, blah, blah, blah. The dot symbol says use everything in this data set, which is really handy because typing out all 26 column names is kind of a pain. So I'm going to do comma, and then you have to tell it where the data is, so data equals final. Alright, so it saves everything in a regression over here, and we're not really going to look at any of these numbers in the same way we will when we actually get to regression, but it just saves everything for you so you can do other stuff with it. And I'm going to make this a little bigger on the plots because we're about to do some plot pictures. There we go. Okay, we're going to make some standardized residuals. So standardized equals r student, which is a studentized residuals. So we're just going to save those. That means that they're going to be z-scored. And z-scored residuals are much easier to interpret than regular residuals because z-scored residuals should look like normal distribution, while regular residuals look like chi-square. It's much easier to explain the rules of a normal distribution to you. So this helps you look at your assumptions. And then we're going to do this fitted thing. So fitted equals scale. Scale is a z-score function. It will z-score them for you. So for the same reason, the last line, we just have to do this in 2 different ways because there are different numbers we're trying to get out of here. Take our fake data set and use the fitted values. So don't use residuals because we did that already in this line. All right. Now I could, now that I have that set up, let's do normality. And then this part you can do in any order. Okay. After this point, any order you want. I could check for individual normality issues by using the moments library. And what I'd do is I could take the skewness of my final data set and I could do 1 column. I think you can do multiple columns, but what you have to do is be sure you drop any of your categorical columns because otherwise it goes Yeah, there we go. So be sure you're dropping categorical columns, but you can't do them all at once. And so when we're dealing with skew, anything over 3, anything over 3 is problematic. 3 is the 0, 0, 1 cutoff for a z-score. So we don't want things larger than an absolute value of 3. That would be bad. Let's look at kurtosis. It has the same rules. So final, be sure you drop those categorical columns. This is why we spent so much time going over how to partition data. Okay. All right, and so we do have some very kurtotic distributions, so that's not good. So look at these, 4, 5, 7, 6, 3. So these have a very a big problem with people only picking like 2 of the numbers. However, one thing about this is that if I have a larger sample size, so n is greater than 30, I don't have to worry so much. Because of the central limit theorem, which was that distribution bunnies video we watched. The last thing I can do is look at the standardized residuals. Now this will show me all of the normality issues at once. So this is a multivariate normality test, which means I'm looking at all the combinations of variables, which is why we calculated it based on this fake regression. And what I want to do is look at this picture and make sure, okay, not in that ugly view, there we go, that the tallest bars are over 0 and most of the data is between 2 and 2 or 3 and 3, but it's symmetric is the issue. So we want the bars, so like really right here is kind of low, but this in general looks okay to me because the highest bars are over 0 and it's mostly between 2 and 2. You will always have these little dudes out here, like always. So it's okay. You just don't want this to go out to like 6. That would be bad. Okay. So that's normality. Let's look at linearity. Okay. This is a QQ plot, sometimes called a PP plot. So it's QQ norm, standardized. Okay. Now that gives me a plot of the quantiles. So these are the theoretical quantiles. What do that mean? Z-scores. Sample quantiles are actual z-scores of the data, of the residuals. And then to make life easier, I'm going to do AB line 0, 1. That draws me a line with a intercept of 0 and a slope of 1. That just makes the whole thing easier to read. Okay. Generally, you want to make sure between 2 and 2, that's a common theme here, that the dots line up on the line. This is pretty close, so I'm okay with it. You will sometimes have problems out here on the tails, and that's because it's hard to predict people on the ends of the distribution because they're so unusual. But most of the dots here are on the line, so it should be okay. Alright, so homogeneity and homoscedasticity, homo-G-N-S, that's what I always like to call them. We're going to look at a scatter plot of the residuals. So I'm going to do fitted. That's going to be X by standardized. That's going to be Y. You could do them the other way, but this is the common way. So we're looking at the scores that if I predict a random variable, here's their estimate. And if I look at the difference between their estimate and their actual scores, here's what the residual. So this is their estimated score. This is the difference between their estimated and their actual score here on Y. And I want that to look like a bunch of random dots. But that's hard to see sometimes. So if you do AB line 0, 0, you'll get a 0 line across the middle, an AB line V equals 0 for vertical, and I'll give you a line down the middle. Okay. And so what I want to see here for homogeneity is, I used to call this no raining, but I don't know if anybody gets that until you've looked at about 100 of these pictures. Whoa, what just happened? Ah! Go away. There we go. Hopefully I didn't close studio. Ah! What just happened? This never happened to me. Okay, I guess I'm gonna have to close studio. Good thing I hit save a lot. Open studio. See where we at. Okay, good. Let me make my plot again. Yeah. Oh no! Okay, let me rerun everything. And the cool thing is I can highlight all this. It's a good thing about having code. Tell it to run and then just kind of wait. There we go. So you'll see we got a slightly different picture this time. And that's because we miced slightly differently, and we have a slightly different random variable. So if you're unsure, you can also run this graph several times and see what happens. Often it'll be the same picture but slightly rotated because the numbers in the data aren't really changing except for the miced stuff, but the residuals or the random variable that we're predicting is changing, so the dots tend to stay the same distance away, but they might jump quadrants because of the random thing they're being predicted with. They are predicting, rather. Okay, homogeneity. So what we want to look at is across these 0 lines, so the lines we drew on the graph, are most of the data between 2 and 2 or 3 and 3. And so I would say here it is. So if I draw this imaginary line up 3 and 3, and then if you want to get really super creative, you could actually draw the lines at 3 and 3. So you could do vertical equals -3. And then you could do AB line, vertical equals 3. If you just are really having trouble seeing it. So all but 2 of 3 of the dots appear between 3 and 3, and the spread is pretty uniform. This way I'd probably do 2. So AB line, you could do H for horizontal. You don't have to do all these. 0 and 0 really helps, but if you're not good at looking at these and it's fairly new for you, it might help if you draw the lines. It looks crazy now, but most of the data is between 2 and 2. I've got a couple down here and a couple out here, and it's spread pretty evenly. So I would say that this chart's okay. So we're looking for an even spread around 0. Okay. So let me make that graph again, this time without the lines. For homoscedasticity, ooh, don't delete everything. There we go. This is the end. For homoscedasticity, I want to look and make sure this data doesn't make a picture. So if I were to draw a line around it, again, this is not something you have to do, but for some reason people like doing this part. Let me make this a little smaller. So if I were to take and insert a line, inward or whatever, around the data, it should look like a bunch of dots. Right now mine kind of looks like a potato. And so it shouldn't make a shape, and it really shouldn't have, well, one problem we have here is that this part down here is missing. But if I think about the fact that this is only a couple of dots out here and I sort of cut off this piece, oh, I'm terrible at this. It's a little more blob-like if I consider the fact that this extra piece is happening because of these 2 dots, but it's still a little empty down here. So that's slightly problematic, but it's not huge. So you really don't want the dots to make triangles or have issues with looking like a UFO, a megaphone, a Dorito chip. Like, you don't want it to look like something. I have people draw me tons of fun pictures for this when they do the assignment, so if you want to take part, you can. But in general, don't be too strict on this. And when the graphs look really bad, you'll know. And if you want to look at some examples, what you can do is Google heteroscedasticity. Hetero being bad. It's a hard word to pronounce. I've never seen that. Oh, it's on the Stats Make Me Cry website. That's funny. Anyway, so click on images. And then you can look at pictures where people give examples. The most common picture you'll see is this sort of triangle shape, because that's usually the issue, is that predicting we're better at one end than the other in regression style analyses. But you might get this shape as well. It's a pretty common issue. Or this sort of curvilinear shape and implies that your linearity graph is going to be bad. This would be like this bow shape would be bad. So you can look at some examples of problem charts. So after you look at these, ours doesn't look so bad, right? So that would be the end of data screening. You might have a couple of additional analyses depending on the type of test you're doing. So for example, you might do the Levine's test for ANOVA or Box's test for MANOVA. But with those, what we'll do is within each test that we run throughout the semester, we'll talk about here are the data screening rules that apply, and then here are the other things you need to check.